Okay. In the last unit that we concluded, we saw that we proved that the key to achieve error-free communication over a noisy channel, the noise could be in the form of distortion or could be in the form of interference. All in all, we concluded that the key part of achieving error-free digital communication is using or implementing redundancy. Okay, so redundancy was the key, which is actually adding a few digits to the original data bits. Okay, key for, you can say, achieve error-free communication. In fact, since we are talking about digital communication, okay, yeah, since Shannon's famous theorem or his famous paper, a great deal of work has been carried out later out in the area of these error correcting codes, where we will add redundancy at the transmitter such that the code becomes in such a way that even in the presence of noise in the channel, the errors can be detected and corrected at the receiver end. Okay, so in the area of forward error correcting codes, a great deal of work has been carried out. So such kind of error correcting codes, we call them as forward error correcting codes, or in short FEC. Okay, so the error correcting codes that we talk is a class of forward error correcting codes. Further, these FEC codes can be generally subdivided into two major parts. One important class of this FEC codes is known as block codes. Okay, so in case of block codes, as the name itself suggests, that every block of k data digits in here, every block of k data digits in general, okay, is encoded into a longer code word. This code word, in general we call it as of length n digits. Okay, so the key to achieve this is to increase the data rate, as you have seen in the case of Shannon's theorem as well. So the increasing data rate can be achieved by having redundancy bits, by adding extra information over the original data digits. Alright, so obviously here n is greater than k. Okay, so every unique sequence of k data digits, original message digits, fully determines a unique code word of n digits. Okay, so in case of here, I can say a unique, there is a mapping between a unique sequence, okay, of k data digit, okay, fully determines a unique code word is mapped into a unique code word, okay, of n digits. So there is an injection from the data digits to the code word. Okay, so this is in case of the block codes. In block codes, further, it is achieved that we need to wait for k data digits to be accumulated at the transmitter. Okay, so we should wait until I can say wait until k digits are accumulated, and then you need to perform the encoding and then encode. Okay, this is the structure of the block codes. So there is another important class of error correcting codes, okay, so which is known as convolutional codes. Okay, convolution codes, in this case the coded digits or coded sequence of n digits depend not only on the current k data digits but also on the previous data digits as well. So I can say here that coded sequence of n digits, can say n digits, these are the coded digits. Okay, these depend on the k data digits and the previous, I can say if there are n minus 1 digits, but also and also I can say and also on the previous n minus 1. So if there are so many digits which are accumulated, so I can say it also depends on the previous data digits as well. Of course, capital N is obviously greater than 1, right? So we see that unlike block codes where they were just dependent on the present sequence of data digits, but here it also depends on the previous data digits as well, and hence we can say this has a memory. Okay, so unlike block codes, convolution codes come with memory. So this implies that I can say that the coded sequence for a certain k data digits may not be unique. Okay, coded sequence for a certain k data digits may not be unique. Okay, so these are the important properties and differences between the block codes and convolution codes. So in convolution codes, the encoding is done on a continuous running basis rather than waiting for k blocks of data digits to arrive. Okay, so this is a continuous encoding scheme. Okay, so there is no wait. All right, so with these two classes of forward error correcting codes, I say that in communication system 1 course in this semester we will be just sticking on to block codes, and in next part of this course, which is in the form of communication system 2, we will be dealing with convolution codes. Okay, so that's the primary heads up with what is in place for us for next couple of lectures. Okay, all right, so we have seen that from Shannon's that we have studied in last unit, Shannon's noise channel coding theorem. Okay, it states that for a noisy channel with a capacity C, there exist codes of rate. Okay, for I can say for a noisy channel there exists a code with rate of transmission R, which is less than the capacity of the channel. Okay, such that the decoding can lead to, if I implement an optimum decoding procedure, which is known as maximum likelihood decoding technique, which can lead to a probability of error, okay, with probability of error which is lesser than, we have seen this, lesser than or equal to exponential, which is actually written as 2 power minus n EB of R. Okay, this can be proved. Shannon has proved that with an optimum or maximum likelihood decoding technique, and if we maintain the rate of transmission less than channel capacity, then the probability of error in receiving the symbols would be lesser than or equal to which is exponentially inversely proportional to n times EB of R, where R is code rate. Okay, we'll define this code rate, because this code rate is defined separately for block codes and convolution codes, but this expression is common to both of the types of the coding schemes, and n refers for as we have told is number of data digits, number of coded digits, number of coded digits, and here EB represents energy per information bit, energy per bit, or we can say energy per information bit. Okay, this is with respect to binary data. All right, so it seems that for good codes, if I say something like, say for really good codes, okay, if you want to formulate, or if you want to design really good codes which achieve this probability of error, where if I try to tend this probability of error approximately equal to 2 power minus n times EB of R, where EB is a function of the code rate, it seems that the result which would require for good codes would demand large n. Okay, so good codes demand large n, okay, to reduce error probability. Okay, to reduce probability error, because of the fact that for a fixed rate, if I fix a code rate and if I fix the energy per information bit, keeping this quantity fixed, I can only reduce the probability error by increasing the number of coded digits. But what is the problem with this? With this, the requirement, but this requires, obviously, so this requires decoders to use large memory. Okay, this demands for large memory and high complexity. Okay, because of the increasing size of the code words. The key to the problem of designing really good codes, or designing a code for error correction, is to search for a really good code with large length n to reduce error probability. Obviously, we have to have this large n, but as well as the decoders that are simple to implement. Okay, so therefore design of the codes involve design of the codes involve two parameters. One is to keep this large n, but with simple decoding technique. But simple decoder. Okay, so there's a trade-off between these two. Okay, for modern codes like turbo codes and low density parity check codes and other several codes which are used in current digital communication system is really achieve this fact. All right, so we'll try to understand the basic theory involved in designing such codes, and we'll introduce one of the famous block codes known as linear block codes in this unit. All right, so this analysis or this understanding of design of codes requires strong mathematical background. However, the treatment of error correcting codes this semester and next semester is in the order of increasing mathematical complexity. Okay, but however I will not dig deep into the actual mathematical background, but we'll just take what is required and try to understand the procedure involved in it. Okay, so all in all, we have seen that, as I told in the beginning, the redundancy is the key. Okay, redundancy is the key. Okay, let's revisit this redundancy for a couple of minutes. Whatever you have done in the last unit is very similar to the treatment that I will be doing here, but just to refresh and try to take from the point of conclusion, I would try to revisit the concept of redundancy. So in FEC codes, a code word is a unit of bits that can be decoded independently. The number of bits that we have already seen that the code length is nothing but number of bits in a code word. Sometimes we write this as simply as CW. Okay, so let us say that if k data digits are transmitted, okay, so let us say that if k data digits are to be transmitted, we have accumulated so many data digits are to be transmitted. Okay, the transmitter by a code word, the code word which have of length n digits of code word, then we say that the number of digits which are added to the original information digits as redundancy or checkbits. Okay, so we have called the extra digits which are added, which we called as check digits, which is simply n minus k, and we call it as m. Okay, all right. So with that, the code rate, we will define a few of the parameters involved here to take it forward. So the code rate, we define it as R, which is the ratio of the data digits over the code word digits, which is n. Okay, such a code word is known as, so the code word is defined as an n comma k code word, or I can say that such a code, simply a code, I can say it as n comma k. Okay, so we can assume that the data digits being represented as the data digits be represented as vector d, where this has got the digits d1, d2 and so on up to dk, which are k tuple of the length k, and hence this is a k dimensional vector d. Okay, this is a row vector of dimension k. All right. Similarly, a code word. Okay, similarly code word can be defined as C. This is similarly a row vector. C can be defined as C1, C2 up to Cn. Okay, so it's an n-dimensional vector. So as a preliminary, we shall determine two important parameters of this. Okay, let us determine the following two things. So first one is that to determine the minimum number of check digits required to correct. Okay, so let's try to find out what is the minimum number of check digits required to detect the errors or correct the errors. That's an important parameter that we are going to find out. So this is just one of the important parameter. So in order to find this out, we should find out the minimum Hamming distance between the code words which will help us in detecting a certain number of errors. Okay, so we have seen from the earlier theory in unit 4, if the binary code length is n. Okay, so we'll stick to our discussion to binary. For a binary code length n, okay, we'll have 2 power n combinations, or there will be 2 power n code words, or these define graphically the vertices of n-dimensional hypercube. Okay, so graphical view of this would be the vertices of n-dimensional hypercube. Alright, so similarly, how many data digits that we have? So we have the available data digits with us is k. Okay, and hence we can say there are 2 power k data words combinations. Okay, so these are the vertices which actually occupy the n-dimensional hypercube, right? So that these are the available vertices. So I can say there's available vertices. This is the occupancy of vertices. Alright, so these are things that we know already based on the graphical perspective of redundancy. Okay, in this case, if we try to transmit, say, a particular data word, say for example, if I try to transmit a particular data word dj by using any of the code word in the set. Okay, so if I want to transmit d suffix j for any j using a code word, say cj, if there is no noise in the channel, then definitely I will receive such a code word which can be uniquely determined by the decoder. But due to noise in the channel, this transmitter, okay, these are the transmitter in the channel, due to the noise, obviously the received code word will not be cj, but it will be something like cj dash. So this is at the receiver end. Okay, our job is to map this Cj dash. Even with the case of error, we should rightly map it to the original data digits, which is dj. So graphically we can say that because of channel errors, the received code word definitely will fall in within the somewhere within the Hamming sphere of radius t centered around Cj. Okay, so Cj dash is a point inside the Hamming sphere centered around Cj. Okay, obviously this is of radius say t, where t represents the number of errors. Okay, where of radius t, where I can say that if where t represents the number of, where I can say number of errors is represented by t, or I can say simply number of errors. Okay, this will be easy to understand. So the number of errors is not number of errors in digits, I can say in digits, is lesser than or equal to t. Okay, if the point is is in the Hamming sphere of radius t, which has a center around Cj, then definitely the received code is erroneous, but it has an error which is in the form of number of errors in digits, which is number of errors in the digits is less than or equal to t. Okay, so if the code is designed in such a way that it can correct up to t errors, then the code must have the property that all the Hamming spheres of radius t centered at the code words are non-overlapping. Okay, that's what we had said, right? So this implies that for a code to correct, can say for a code, yeah, to correct up to t errors, okay, must have the property that that all Hamming spheres of radius t centered at Cj are non-overlapping. Okay, then only we can uniquely determine what is being transmitted. So this is one of the important property of the error correcting code. This is the graphical perspective that we have seen in case of the introduction to redundancy, the role of redundancy as well. So this demands that we have seen that such codes can be placed on the vertices of any hypercube, any n-dimensional hypercube, in such a way that the minimum distance, or we call it as Hamming distance, between two code words should be maximum. In the sense, say for we have seen that if a code word is designed such that it will correct one error. So how many times we try to repeat such one single bit? We try to repeat for 3 times, odd number of times. Okay, so we have seen that if I try to repeat 3 number of times, there were 8 possible combinations, but if I want to have non-overlapping Hamming spheres, one would be centered around 000, another was centered around 111, and the Hamming distance between those two was 3. In the sense, this implies that d min, or the Hamming distance, was 3. And I also stated that for t is equal to 2, okay, so we will repeat 5 number of times, odd number of times, and hence the Hamming separation between them was actually 5, and so on. So this implies that we can write the property of such a code which will correct up to t number of errors in digits. In general, for such a code, the minimum distance between code words should be twice of t plus 1. Okay, so this is the one of the important property of the error correcting codes. Okay, so where d min indicates the minimum distance between t error correcting code words. Okay, so d min indicates the minimum Hamming distance, of course. Okay, minimum Hamming distance between t error correcting codes. Okay, so this is one of the important criteria as we try to find out our aim is to find out the number of check digits required to correct up to t errors. Okay, next our job is to find a relation between n and k, which will give us implicitly will give us the number of check digits to be added. Okay, to find relationship between n and k. Okay, so we observe that there are 2 power n vertices available, 2 power n vertices available. Okay, and 2 power k vertices are occupied. This I have written earlier. Vertices are occupied. Okay, so this implies that there are 2 power n minus k redundant vertices which are unused. Okay, or I can say which are added as extra check digits. Okay, so the question here is how many vertices out of these, or how many vertices or words can lie within a Hamming sphere of radius t. Okay, so to answer to this question, the number of sequences is n digits here, which is a code word length from a given sequence of j digits, which I want to find out. Okay, so if I try to write the number of sequences, okay, say of n digits that differ from a given sequence, by say j digits. Okay, so if I want to find out say in a sequence if there are n digits, what would be the number of sequences that differ from each other by j amount of digits. okay, at a time. So this is given by, obviously, how do you say this? I can say that the number of possible combinations of n things out of which j are j digits are different. Alright, so it's a combination of all possible combinations, which is n digits, out of which the j number of digits are different with each other. Okay, and hence this is the number of ways in which up to t errors can occur. Okay, so this is the number of ways up to t errors can occur. Okay, so this for each code word, for each code word which is mapped to each block of k digits of original data, we must leave therefore I can say this is for one case. Thus for each code word, in our case, therefore for each code word we must leave how many now? Up to t errors. So t errors is starting from 1 to t and cj. Alright, vertices, okay, or words, the code words unused. Okay, but we have how many code words we have? We have got total of 2 power k code words. Therefore we must leave a total of 2 power k times j1 to t and cj. Okay, so must be unused. Words unused. Okay, so that means that therefore the total number of words must at least be, right? So this is the code word number of code word lengths, which is 2 power k. We should have so much amount of words as an addition, 2 power k times j1 to t and cj, right? So which I can write this as j from 0 to t, simply 2 power k, which I take as common, and cj. Okay, but we have the total number of vertices that is available with us is 2 power n. N is the number of the code word length, right? So the available vertices is 2 power n. So with that I can say but 2 power n, which is the number of available vertices, which must be greater than or equal to, this is the total number of available the vertices in the hypercube. Obviously this must be greater than or equal to 2 power k times j0 to t and cj. Alright, or so this can be rearranged as 2 power n minus k must be greater than or equal to j0 to t and cj. j, or we have, since we have said this n minus k is number of check digits as m, so this implies that 2 power m must be greater than or equal to 0 to t n cj. Okay, so this bound on number of redundant digits, the first question that we started off with this part is how many number of check digits are required to detect and correct the errors. The number of errors that needs to be detected and corrected is limited by the parameter t here. So for such number of errors which can be detected and corrected is governed by the number of redundant digits that we are going to add up to the original data digits, which is represented by the parameter m here. So this bound on redundant digits. Okay, so this is an important expression. So I can say that, so this is actually known as, since it's based on the Hamming distance, this is known as Hamming bound. Okay, so it should be remembered that the Hamming bound is a necessary condition but not sufficient condition, because of the fact that it doesn't give us how and in what way we should be adding the redundancy digits. Okay, so such that, so this is I can say that this is a necessary but not sufficient condition. Okay, so it does not necessarily mean that the t error correcting code of n digits can be constructed. Okay, so for any n and for any m we cannot construct such codes which will correct the number of errors as a t. Okay, so there are possible set of the codes which will detect and correct up to t number of digits, and hence except for this, probably for the simplest case, this would be both necessary and sufficient condition. So except for single error correcting code, except for t is equal to 1, which is actually a single error correcting code. Except for this case, we'll have a condition which is governed by Hamming bound is necessary but not a sufficient condition. Okay, so when would this inequality be equal? So for some cases, okay, for few cases, this 2 power m would be equal to j 0 to t n cj. Such codes are called as perfect codes. Okay, these perfect codes are also not so difficult to achieve, although it gives a perfect equality between these two quantities. But you must graphically understand that in such codes, Hamming spheres obviously will be non-overlapping, not only non-overlap, okay, but they occupy all 2 power n vertices. Okay, So we have said that there are at least few vertices which are to be unused. That is the statement which leads us to inequality. But in the equality case, all the vertices will be unoccupied. But also remember that with the radius t, the Hamming spheres will also not overlap with each other. Okay, so and hence it is called as a perfect code. Perfect codes exist. This is not just a theoretical in definition of perfect codes. They do exist, but for a very few cases. Okay, compared to the other the list of all other error correcting codes, these are very few cases which give us perfect codes. Okay, and the single error correcting code sometimes is called as the single error. Okay, some our explanation or probably our the theory involved in error correcting codes would revolve around single error correcting codes. Okay, whenever we take example which will be simpler to take, we call such a single error correcting codes are called as Hamming codes. Okay, so Hamming codes are such codes where t is equal to 1. Okay, so this implies that 2 power m is equal to j 0 to 1 ncj, which is nothing but nc0 plus nc1. nc0 is 1 plus n, correct? So with basic theory of the combinations definition. Okay, and this means that n is 2 power m minus 1. Okay, all right. So Hamming codes are represented as n, k. All right. So with n is equal to 2 power m minus 1. Okay, and what is k? K is nothing but n minus k is m, so k is n minus m, so which is nothing but 2 power m minus 1 minus m. Okay, so and with the minimum Hamming distance between the codes is obviously is m, which is nothing but the number of check digits that we have added to original digits. Okay, so one of the most well-known Hamming code is Hamming code is is 7 comma 4 with m as 3 with a separation of with the minimum code separation of 3. Okay, there are other possible n comma k code words as well, but this is one of the famous and well known Hamming code. All along this discussion we have talked about FEC codes, where it was about forward error correcting codes. The classes that we defined as block codes and convolution codes are classes of forward error correcting codes. In the sense the receiver doesn't give back any information to the transmitter that it has detected and corrected codes, right? But there could exist some systems which is not part of our discussion, but just to state that there is another class of mechanism which is known as ARQ. Okay, this probably would be the part of computer communication networks, where the transcender and the receiver will acknowledge or kind of exchange handshake signals to say that it has detected and corrected errors. Okay, so such that this is known as, in fact, automatic repeat request codes. Okay, mechanism is automatic repeat request. It's not a class of codes, but this is the system that is involved in most of the computer communication networks. Okay, so because error detection, unlike correction, error detection requires fewer redundancy bits. Okay, so remember that. Okay, remember that error detection requires fewer check digits than that for error correction. Okay, in case of ARQ mechanism, the receiver doesn't this receiver job is to just to detect the errors but not to correct. It just sends information back to the sender that there is an error that occurred in sending the data or sending the packets. Alright, so in such case, when when n is lesser than what was originally required for error correction, obviously this implies that the n over k dash, sorry, the code rate, okay, the code rate for this scheme, which I can call this as r dash, k over n, where n is not the scheme for error correction, but just for error detection. Obviously this code rate would be definitely greater than r, and hence there would be increase in efficiency. Okay, alright, so redundancy is reduced and hence the efficiency is increased. Okay, in such schemes, the minimum having distance between the code words would be simply t plus 1 in case of error detection but not correction. Okay, so that is one of the important aspect of these ARQ schemes. Alright, so we'll use mostly, in this course we have just will be developed based on FEC codes, in particular with respect to block codes, and this would be sufficient to understand the classical forms of block codes like linear block codes and cyclic codes, which will be dealt in next sessions here onwards. Thank you.